Hi, my name is Neha. It's my honor and privilege to be giving this talk. Thank you to Yakir and Sharon for this kind invitation. I'm very excited to talk about the work we've been doing in the past few years at Amazon. I believe we are entering the golden age of automated reasoning, and I hope by the end of this talk, you believe that too.
Here is the flight plan for the talk. We're going to kick off by talking about the automated reasoning work happening across Amazon. Then we are going to zoom in to the verification of access control at AWS and how to get to a billion queries. What were our pillars? The three pillars on how we eliminated specifications, did domain specific abstractions, and SMT solving at cloud scale to make it happen. Amazon has made significant investments in developing and applying formal tools and techniques to prove the correctness of critical internal systems and provide services to end users to prove correctness of their own systems. You can read a lot about the work we've done across the publications that we've had in the past several years. You can also watch talks on YouTube given by AWS customers on how they are using automated reasoning based tools and services. To get to these talks and papers, we have a provable security website. So I want to point everyone to go here and get to the papers as well as the talks. There is also an automated reasoning section on the Amazon Science webpage. The same information on papers, the latest ones, will also be available there.
Today, my talk is going to focus primarily on access control and describe key milestones in our journey of generating a billion queries a day. It's all in the context of verifying access control. But before we get started, I want to provide a quick overview of all the work happening across different domains at Amazon across the entire computing stack.
So let's take a quick tour of where we apply automated reasoning techniques in AWS. We're going to start with foundational code. There are numerous foundational systems in the AWS cloud, such as custom hypervisors, encryption code, bootloaders, and an IoT operating system. We use bounded model checking to verify memory safety properties of the boot code running in AWS data centers and of real-time operating system used in IoT devices. FreeRTOS is an open source real-time operating system for microcontrollers that makes small, low-power edge devices easy to program, deploy, secure, connect, and manage. Last year, it was downloaded every 170 seconds. So, proof of memory safety, thread safety, and the functional correctness of the free RTOS concurrent queue implementation is available online. It provides a high level of assurance for the free RTOS interprocess communication mechanism, which uses these data structures. Again, the proofs are publicly available and run as part of the continuous integration to help ensure the continued maintenance. Another example of a foundational library is BigNum, which is used for high precision integer arithmetic, that is around 1,000 bits. Most asymmetric public private key crypto systems like RSA use these BigNum libraries. It is used in S2N. S2N TLS is an AWS implementation of the TLS SSL protocol that is designed to be simple, small, fast, and with security as a priority. There is yet a proof that is it publicly available to show that it is free of side channel attacks. As we move up the stack, we leverage automated reasoning to make sure that the protocols used in the cloud are correct. AWS KMS is a managed service that allows customers to manage cryptographic keys and control its use. We use proof assistance such as EasyCrypt and domain specific languages such as Cryptol to verify these cryptographic protocols. There's a machine checked proof that the cryptographic keys protecting customer keys are maintained securely across AWS server. The connection of the code to the protocol is continuously checked, and the protocol description and proofs are open source and they can be independently verified. Now, we continue to move up the stack and to how we leverage automated reasoning in AWS. Here, we make sure that the applications are secure and correct. We want to ensure, for example, that all internal services that handle customer data are doing it securely. For that, we do data flow analysis to ensure that the service code, that all customer data is encrypted before it's stored, logged, or passed to another service. We also have customers in Amazon. So last year on Amazon.com, we sold over $386 billion worth of products to customers. And one of the things that this requires is the ability to safely and securely store critical payment information for our customers. We want customers to trust us when they enter their data into one of these forms, and we want to continually earn and maintain that trust. At Amazon, we are building a secure payment vault on AWS, and we are using automated reasoning to verify it.
There is a lot of exciting work happening across Amazon using tools and techniques developed by you and others in the automated reasoning community. Before I get to the core of the talk, I'm going to do a quick cloud computing 101.
So, Amazon Web Services is a cloud computing service provider that has made significant investments in applying formal methods to proving correctness of its internal system and providing assurance of correctness to its end users. So, what is cloud computing? It is an on demand delivery of IT resources via the internet with pay as you go pricing. A way I ask people to think about it is about programming with a new function, a function f whose return type is a computer. The functions we've used in programming before return things like integers or booleans or files or sockets. But now you have a function that returns a computer. What would you do with it? You could invoke the function a bunch of times to get other computers. That's certainly fun. But what's more interesting is how you would program with this function. For example, suppose you're building an application that uses a database. When the utilization of your database gets high, your system should call this function, get a fresh computer, shard a part of the database onto the new computer, and scale up. Later, when the utilization drops, you have this wonderful F inverse that takes the computer and gets rid of it. With these two functions, your system enables the user's database to scale up and down automatically. So, a lot of people want this kind of functionality for their databases. So, AWS provides a combinator or wrapper around F and F inverse. This combinator acts like a function whose return type is a highly scalable database. The AWS console, as it's called, is a web page that lists hundreds of these services available through AWS. Here's a few of them covering use cases of compute, developer tools, application integration, storage, media services, and databases. This list can be initially daunting, but remember, these are just functions with powerful return types. For example, here's the Lambda function, which lets you run code without managing services. We can think of this as a combinator. When it's invoked, creates a server, runs your code, and then destroys the server. Semantically, it's just F inverse composed with your code composed with F. This is called serverless computing because the computer is abstracted away by the combinator. When 1,000 requests come in the same way, 1,000 computers are created, used, and destroyed. It's the kind of thing that's possible when computer become objects in your programming language. There's other functions here that provide you reliable queuing, durable data storage, and fast key value databases. More combinators for more use cases. Billion is a big number, and I promised you a billion queries. So, this talk describes our key milestones in our journey for generating a billion SMT queries a day in the context of AWS Identity and Access Management, IAM. So, IAM is a system for controlling access to resources such as applications, data, and workloads in AWS. Resource owners can configure access by writing policies that describe when to allow and deny users access to the resource. And these configurations are expressed in the IAM policy language. To help AWS users secure their resources, we built a Zelkova, a policy analysis tool designed to reason about the semantics of AWS access control policies. Zelkova translates these policies into SMT formulas and then uses SMT solvers to prove a variety of security properties. It can let users ask questions such as, can Neha launch EC2 instances outside the US? Is my bucket publicly accessible? Is this admin user required to use two-factor authentication? And to do this, Zelkova uses a portfolio solver. It invokes multiple solvers in the backend and uses the results from the solver that returns first in a winner take all strategy. And this really allows us to leverage the diversity among solvers and quickly solve queries, a couple of hundred milliseconds to tens of seconds. The SMT encoding uses a theory of strings, regular expressions, bit vectors, and integer comparisons. And the use of wildcards, any number of characters, and question mark exactly one character in the string constraint makes the decision problem piece space complete. You can read about the details of how we encode it in our FMCAD paper. But there is a whole set of AWS services that integrate with Zelkova. They are detective controls, corrective, and preventative. We have examples from Amazon S3, which is an object store, AWS Config, which is a change-based resource auditor, Amazon Macy, which is a security service, Trusted Advisor, Amazon Guard Duty. And Zelkova drives these controls across a large set of customers and a large set of services. So here's an example. Zelkova drives this public badge, which is a detective control in the S3 console. This is an example of more what I would call formal methods a la carte. We have a whole bunch of controls developed around Zelkova that is available in a service called AWS Config. We also have customers building checks based on Zelkova. Here, it is to do an automatic detection of changes to ensure that the policies do not get more permissive with changes. And these customers have then put it in their CI CD pipeline to ensure that the access controlled is versioned and code reviewed at every segment. This makes it a powerful capability for our customers. It powers preventative controls such as S3 block public access. At the last time that results were published, it handles 1.1 million requests per second. And this is in 2013, where it took less than a year to double the numbers. And now S3 doesn't even publish these numbers. So, how do we integrate a formal methods tool in the request path of a high availability, low latency tier one service? And the answer is very carefully.
Launching block public access was a watershed moment for the cloud, for security, and for automated reasoning. We now had an automated reasoning engine in the request path of an S3 API. This was an inflection point for all we could do with automated reasoning. It was now a part of computing, a fabric, a must have. And in the next section, I'm going to talk to you about how Access Analyzer took it to that next step.
At the end of 2019, we launched an AWS feature called IAM Access Analyzer, which uses predicate abstraction to help users verify the access control policy. Now, here's the launch announcement where we call out automated reasoning as the engine for this work. Putting this power in the hands of everyday users had been a journey for us. And most automated reasoning tools require serious expertise and effort. And Access Analyzer requires neither. And in this talk, I'm going to show you how we did this and how it led to a billion queries. I'm going to talk through a fundamental change in our approach to user facing automated reasoning. We moved away from the traditional approach where users do all the work upfront to specify their intention towards a new approach where the machine does the specification upfront and the user layers their intentions on top of it. So, how could we eliminate writing specifications? Zelkova follows a traditional verification approach. It takes as input a policy and a specification, and it produces a yes or a no answer. It is important to understand who's doing the work here. One human, usually a developer, writes a policy. Another human, often a security engineer, writes a specification of what's acceptable. And the machine does the verification and returns a yes or a no answer. And this approach works, but it's hard to scale so that everybody can use it. The bottleneck is right here. It's the human effort it takes to specify acceptable behavior. And no, it's not the human's fault. We know it because we've tried a lot of different types of humans. We've had security experts writing specifications, we've had consultants work with security teams to write specifications. But again, it doesn't scale. And we've written our own general specification that can be used by everyone. And for example, check if the S3 bucket allows public access. But beyond a few general checks, the customer is different and general specifications only go so far. So, how did we change it with Access Analyzer? We made the machine responsible for specification. We have the machine put in the upfront cost. We have the machine returned a detailed set of findings. And then only at the end, the security engineer is the one who takes these findings and returns Booleans. So, what's the meaning of these Booleans? Because the findings are produced by the machine, they are already verified to be true. So, why do we still need a human there? The human is deciding if the findings should be true. The human is making a judgment call, expressing intent. This is exactly where we want the human expertise to be focused on. We want security experts to be making security judgments. So let's think about how we can make this approach work. What do we need from findings? First, we need to be able to trust the findings. It's not just enough to identify some of the accesses, we want them all. We need the findings to be sound. If every access is represented by some finding, then we can verify the safety of access by verifying the safety of each finding. Next, we need the findings to be precise, enough. We could get soundness with a single finding that everybody has access, but that's not useful. To be useful, we want findings to adhere closely to the actual access that's allowed by the policy. And finally, we need the findings to be compact. We could get soundness and precision by returning a finding for each of the millions or billions of allowed access, but no human could ever review them. Instead, we want the set of findings to be reasonably small. Now, suppose we call one of those combinators and make an S3 bucket to store your critical files. Then you'll want to control permissions on this bucket. So the only right people have access to the bucket. AWS lets you do this by attaching a resource policy. Let's look at an example policy and we'll build it up in pieces. So to start, when the policy is empty, there is no access allowed to the resource. It's secure by default. We add an allow statement to grant access. This one grants access based on the virtual private cloud or VPC where the request originates. You can think of a VPC as a network. This statement says that any requests from VPC-A or VPC-B are allowed. Now, we add another allow statement to grant additional access. This one grants access based on the organization ID of the requester account. An organization in AWS is a group of accounts, and the organization ID is the unique identifier. So this statement says that everybody from organization O2 has access. Finally, we add a deny statement. This statement removes access granted by the allow statements. It uses a conjunction of conditions, one of which is negated. So let's look carefully at what it's saying. If the request originates in VPC-B and the requester is outside of organization O1, then deny access. So here we can see the combined effect of all of these policy statements. This is where stratified predicate abstraction comes in. To see how, let's think about findings. What should these findings look like? What should be their language? Ideally, findings should be in the terms that are relevant to the way access is controlled. Looking at this policy, for example, we can see that one of the ways access is controlled is via source VPC condition. So let's extract a set of predicates for these variables. We have ptop, which says source VPC doesn't matter. We have PA and PB that restrict to source VPCs A and B respectively. Similarly, access is controlled to principal org ID condition, and we can extract predicates for that variable. These predicates are the policy-specific building blocks of our findings. Now, how do we put them together? The simplest way is to conjunct them. With this predicates, there's 9 sensible cubes of conjunctions we can form. Here they are laid out in a 3x3 grid. In the top left, we have the most general finding that everybody has access to everything. As we move to right, we can get more specific findings like organization O1 has access. As we move down, we get more specific findings like organization O1 coming from VPCB has access. These cubes are all possible findings we can return. So now what's left is to select a sound, precise, and compact subset of them. The idea is to maintain a sound and compact set of findings while refining the precision of these findings. A sound and compact initial set is a single finding that everybody has access. Could this be made more precise while preserving soundness? Can we replace this finding with these 4 more precise findings? In this case, yes, every access allowed by the policy and by the finding ptop and qtop is allowed by one of these more precise findings. So we can remove the ptop and qtop finding. Next, what about PA and qtop? Can this finding be replaced by these more precise findings? In this case, no. Imagine a request from VPCA and organization O3. This would be allowed by the policy and by PA and QTOP finding, but not covered by either of the 2 highlighted findings. Thus, the finding PA and QTOP is essential. It will be one of the final findings we return. Moreover, the 2 more specific findings will not be returned. Those findings are already covered by PA and QTOP. We continue the process in this way. In the end, we come up with these 3 findings. Here they are written out. We have sigma 1, which says VPCA has access, sigma 2, which says organization O2 has access, and sigma 3 that says VPCB with organization O1 has access. We formalize our algorithm in our CAV paper in 2020, and we show that it achieves our desired properties for these findings. And I'm going to give you a taste of the formalism here, but I'm not going to define all the symbols. The details are in the paper. We formalize soundness in a property called coverage, which says the set of accesses allowed by the policy is a subset of the accesses allowed by the findings. We formalize precision in a property called irreducibility, which says that every finding represents some access which is not covered by more specific findings. Finally, we formalize compactness in a property called minimality, which says that removing any finding from the result shrinks the set of accesses allowed by the findings. It's also instructive to see how closely we achieve our informal properties of sound, precise, and compact. Here's a policy, and the actual accesses are shown in green. Here are the findings shown as bolded white borders. The bold borders surround all the green areas, the shaded areas, so our findings are sound. There are only three findings, so our findings are compact. Now, what about precision? We are almost perfectly precise, except for this one spot here. There are accesses here that are not allowed by the policy, but which are covered by the findings. To fix this, to improve precision, we would need to introduce negation. And in practice, we found negation to be a source of frequent confusion for end users. So, for that reason, we sacrifice precision for the sake of simplicity. And it's going to give a lot of heartburn to a lot of people sitting here to say, wait, no negation? But yes, that's the sacrifice we will make to make it easy for our end users. So, another great thing about findings is that they're modular. Each finding can be understood on its own without the other findings. Contrast this with the policy where the allow and deny statements interacted with each other. So, the modular findings allow security engineers to address them individually. For example, they may look at through these findings and decide, yes, this is acceptable, no, this is not acceptable. And I'm not sure on this one. I need to go talk to the developers and figure out if this access is really necessary. And the security engineer can do the part of the verification and put the other part on pause. Modular findings enable for modular decisions. And finally, this is more subtle, but the findings are always sensible. For example, take this policy, which allows access based on principal org ID. It grants access if the org ID is 123, 456, or 78 star, where the star is allowed to match anything. This is syntactically legal, but semantically nonsense. Organization IDs are assigned randomly, so the notion of every org whose ID starts with 078 is semantically gibberish. In the traditional verification approach, nothing stops you from verifying the supposed correctness of this policy. Your specification can be as semantically questionable as your policy. But in our approach, we control the specification language. In this case, we only generate these predicates. In particular, there is no predicate for this dubious notion of orgs starting with 078. When our algorithm asks, can a finding be generated uh, for these and the more specific findings, the answer is no. There are accesses coming from 7, 8, 9, which are allowed by the policy, and Q top, but not by the more specific findings. So the finding you end up with is that everybody has access. This isn't precisely true, but it's morally true because you haven't restricted permissions in any meaningful way that provides broad public access. And findings are sensible by design and they guide users in making sensible decisions about access control. To make this really usable, we design domain specific abstractions, not just a pretty UX, but domain specific abstractions. This is what the actual Access Analyzer service looks like. This is the landing page for it. Take a look at the workflow for the users. They start the service, review the findings, and take actions. What's really going on here is that users are telling us their specification interactively. They're doing formal verification without even knowing that it's formal verification. And we've had great engagement with this approach. Here's the findings overview page. I've attached our example policy to one of my S3 buckets, and we see that there's three resulting findings here. In fact, these are just our cubes of predicates in pretty printed form. Users can click on a finding to see more information. Here's the detailed page. Here's the predicate again. It gives you more additional information about how the resource is shared, how long it's been shared. And if the user decides it's intentional, they can archive it. Or if the user decides it's not intentional, they can go fix it. And we're going to talk a little bit more about how this process works in the next section.
To truly democratize automated reasoning, we have to think about the end users. How can we have all users leverage the power of automated reasoning without needing to understand logic, be logicians, or even be computer scientists? That was our goal. And I would like for you to see how we accomplished it, how we designed different domain specific abstractions with a consistent experience across different capabilities.
One of the keys to the success of automated reasoning at scale has been to make it easy and relevant for our end users. Something that has resonated well with the customers and end users is how automated reasoning helps them make universal statements of their security. They can make statements such as, my S3 buckets are not publicly accessible. There is no unintended external access to my S3 buckets. All my EC2 instances are not publicly accessible, and all my SSH traffic to my instances goes through a firewall. And the way we talk about it with our customers is that the value proposition is that each of these statements cover the universe of possible IAM requests or the universe of all possible network packets. This is how we explain and talk about the state space exploration problem. But for the end user, it's very easy. They go to the S3 console to look at the permissions for a bucket, and then they see S3 block public access. And as the name suggests, when they turn it on, it blocks all public access to their bucket. It does it by applying this internal lockdown policy to prevent any access from outside their account. But they don't have to go and figure out the nitty gritties of it. It's one click. They can even do it broader. They can enable it at the account level, which applies to every bucket in every region in the account. And when they create new buckets, it automatically applies to them as well. It's easy peace of mind. Now, as an experiment, let's see what happens when they try to break this. Let's say we turn on block public access, but then somebody tries to change the policy to open up public access. For starters, it warns them that this isn't going to work. And because block public access is turned on, so don't bother it. But if they ignore it and try to do it anyways, the policy attachment will fail. When S3 block public access is turned on, there is no way you can make the bucket public. That's the power that automated reasoning provides the users of the cloud. It provides them the bedrock of something they know to be true. Now, to make the universal statements even broader, we've talked about Access Analyzer, and they can go turn it on in the IAM console. When they enable Access Analyzer, it scans their account or organization for the supported resources. And for each category of the access, it says, hey, here are the findings. And the two findings says the first bucket is writable from an external account, and the second bucket is readable from an external organization. So what do they do with these findings? And there is a way to zoom into the finding, and the detail page says if the access is intended, then they can go archive the finding and then it won't show up in their active findings. They can still see it, but it never goes away. but now it is clearly marked as intentional. On the other hand, if the access is not intended, then the customer can go remove it. Access Analyzer directs them to the S3 console for the bucket where they can edit the policy and remove the access. Once they've changed the policy, they can hit rescan to immediately reevaluate the finding. And if they've fixed it, it'll change from active to resolved. Now, Access Analyzer also constantly monitors policies for changes. So if they could have just waited a few minutes for the finding to update on its own. And when the findings get marked as intentional, the end goal is to get to zero active findings. And the zero active findings means that there is no unintended access to the S3 buckets. Now, you see all of these things, all of these processes, whether it's rescanning, continuous monitoring, all of these are generating new SMT queries in the backend to check for the properties. Now, there's other ways that customers can also interact with it. They give you the versatility of looking at the finding to decide what to do with it. They can use a Lambda function to do a risk assessment and decide how important the finding is. If it is a low risk finding, then the Lambda function can archive it. If it's a medium risk finding, then the Lambda function can send a descriptive email to the right team for it. And if it's a high risk finding, the Lambda can go to S3 and roll back the policy. And I'm not going to go into the architectural details of setting this up. I want to show you that the findings generated through automated reasoning is now creating programming opportunities for the end user where they do not have to understand logic or SMT solving, but they can decide what specific actions they can take on the behalf of their company and their security needs. I've talked about Access Analyzer in the context of S3 buckets, but it supports many different resources shown on the slide. Another example of a service is Amazon Inspector. It's one click to enable. And Amazon Inspector scans EC2 instances and containers to identify vulnerabilities and misconfiguration. It, it does it through doing a network analysis. And I've not talked a lot about that in this talk, but it's just important to know that there's many such applications. The types of findings that we're going to focus on are internet accessibility findings. Here it shows that one of my EC2 instances is publicly accessible on port 22. Zooming in, I can see exactly when this was discovered, where the instance is running, what image it is on, and so on and so forth. And again, the goal is to get to zero active findings. So we need to make a decision here. If it's not intentional, we need to fix it. The details pane gives us starting points for where we can go change the ACLs, the route tables, or security groups that makes this access possible. If it is intentional, we can create a suppression rule for it. I'm okay with an instance being publicly accessible on port 22 if it's a bastion host. It's an easy enough filter for that to apply the suppression rule. Now, once I've done this, I can see that I have no active findings. It's the same story as before. When I get to zero, I can state that none of my EC2 instances are unintentionally public. It's a powerful feeling. It's a powerful capability to provide to your customers. Again, they are doing logic underneath, but they don't have to be logicians to do it. Now, customers can program around inspector findings just like they could with Access Analyzer findings. But I'm going to show you another option here. There's something called Security Hub, which is a central place to aggregate and act on findings. And you can see from this architecture diagram, it doesn't get much easier. And here is what the Security Hub dashboard looks like. Notice that it's aggregating my inspector findings as well as my access analyzer findings. So it provides you this ability to compose the different universal statements, to compose the different properties you're trying to verify across different parts of your architecture and bring them together. Now, let's imagine we want to build a network that looks like this. I'm going to give another example. Here we have two subnets, both fronted by a network firewall. And from this picture, we can see that all network traffic goes through this firewall. So we're done, right? Not exactly. So this is just a picture. Let's check that the reality matches this picture. To do this, we're going to use VPC Network Access Analyzer, which is available in the VPC console. It's right next to the Reachability Analyzer, which I'm not going to talk about today. But Reachability Analyzer helps you figure out why instance A cannot talk to instance B. And it's backed by the same reasoning logic as the services we are talking about today. But we're going to look at the Network Access Analyzer example. It's built on this notion of scopes. A scope is a way of saying, show me all the paths from A to B that don't go through for C. And we want to see all the paths from an internet gateway to an instance that does not go through a network firewall. Once we've created the scope, then we can analyze it. Clicking off this button just kicks off the analysis. It goes through all my VPCs to identify every internet gateway, every instance, every path between them, and then filters out the ones that only go through the network firewalls. Of course, it uses SMT solving in the backend to do it. Now, when the analysis is done, customers get a pretty summary of all the paths that match the criteria. Pulling up the details on this path, we see that the hop goes through from the internet gateway through the route table, the access control list, the security group, and then finally the network interface. Clearly, there's no firewall along this path. So when we hover around the network interface, we can see the details. So that means our actual network looks like this. The SSH traffic from the internet gateway to server 3 is routed around the network firewall instead of through it. And the universal statement that the customer thought they were trying to hold does not. Now, there's a lot of these. I've just scratched the surface of all the things that are available to our customers. When you go to the Network Access Analyzer console, there's suggestions on how to get started. It's like a tasting menus of property for customers. They can make universal statements about ingress and egress and trusted networks and restricted traffic and segmentation or choose their own adventure. And if you're serious about knowing the security posture of their network, customers really use Network Access Analyzer. Now, these sets of powerful tools, techniques, which are easy for our customers to use and relevant to them, are all leading to the billion SMT queries a day.
There is a lot going on with these services. The key here is all the action happening on the service side is creating many SMT queries. When you create a new resource, when you onboard a new service, when you make a change, and even when services like Access Analyzer do an anti entropy scan to make sure that all changes are covered. All of these are creating SMT queries in the backend, and that's what's getting us to a billion.
The use of SMT solving in AWS features and services means that millions of users are relying on the correctness and timeliness of the underlying solvers for the security of their cloud infrastructure. So, we've studied the challenges of the correctness and timeliness in solver queries in our community, but we've often treated them as independent features. And today, when we are generating a billion SMT queries every day to support the variety of use cases that we talked about earlier, what we've discovered is that there is an intricate dependency between correctness and timeliness. So Zelkova uses a portfolio solver to discharge its queries. When given a query, Zelkova invokes multiple solvers in the backend and uses the results from the solver that returns first. It's a winner takes all strategy. And the portfolio approach allows us to leverage the diversity among solvers. And one of our goals is to leverage the latest advancements in the SMT solver community. Like solver researchers are fixing issues, making improvements to the existing features, adding new theories. And specifically, our original goal was to replace CVC4 with CVC5 because we wanted to leverage the proof checking capabilities of CVC5 to ensure the correctness of unsat queries. Now, before we do that, we perform extensive offline testing and benchmarking to gain confidence in the correctness of the answers, performance of the queries, and ensure that there are no regressions overall. Now, to check this timeliness constraints, we ran a bunch of experiments across our benchmarks, comparing the results of CVC4 to that of CVC5, a particular version, point 4. And these results are representative over a set of queries. In the graph, we have approximately 1,500 queries that are generated by Zelkova, and we selected a distribution of queries that are solved between 1 second and 30 seconds. And the 30 seconds is the time bound after which the solver process is killed and a timeout is reported. Now, you can see in this graph that some queries that are not solved by CVC4 within the time bound of 30 seconds are now being solved by CVC5, as seen along these points in the graph. However, CVC5 now times out on queries that were previously being solved by CVC4, as we see by the points on the top of the graph. So we worked with the CVC5 developers, debugged the issues, and fixed it that was causing these certain queries to time out. But even with this fix, CVC4 was 2x faster than CVC5 for many of the easier problems that take about 1 second to solve. And now these results are not surprising given that the problem space is computationally hard and there is an inherent randomness in search heuristics within SMT solvers. But this poses a challenge for us, where we are using the results of these solvers in security controls and services that millions of users rely on. A query that used to take 1 second now doubles the time will be visible to the end user and it will degrade the end user experience. So we started looking at options. So we said, oh, how does the new CVC5 solver compare against the winner take all portfolio solver? So this portfolio solver does not include the CVC5 version that we are comparing in this against, but CVC4 is part of the portfolio. And we see it's doing well, even though it does have some of the timeouts. So now we said, let's look at the version with the bug fixed. So here, CVC5 with version 0.7 with a winner take all compared to the winner take all portfolio solver, it's doing even better. So our solution was to add a new solver to the portfolio rather than replace an existing one. We added CVC5 to the existing solvers consisting of CVC4, Z3 with the sequence solver, and our custom Z3 automata based solver. Now, I want to emphasize that when we started the evaluation, we did not plan to add this new version of the CVC solver to the portfolio. We essentially expected the latest version of CVC5 to replace CVC4. And we worked closely with the CVC developers, and CVC5 was better on many queries. It was indeed solving things that CVC4 didn't. But there was still a whole bunch of queries that did not meet our timeliness requirements. And this led to our decision to add CVC5 to the Zelkova portfolio solver. But now the cycle repeats itself because CVC5 had another version, 1.0. And the same question comes up. And we are evaluating it yet again. Do we upgrade the existing CVC5 version with the latest, or yet add another version of CVC to the portfolio solvers? And our early experiments show that there is not a clear answer yet. Now, you could say that a solution that works well in the cloud setting is just having a massive portfolio, sometimes even containing older versions of the same solver. And we could just run this massive portfolio. But this presents us with two issues. One, when we discover a bug in the older version of the solver, we now have to patch this older version. And this creates an operational burden of maintaining many different versions of the different solvers. Two, now when the number of solver increases, we have to ensure that every solver provides a correct result. And checking the correctness of the queries, like when that result in SAT is straightforward. but we need SMT solvers to provide proof of the unsat query. And the proof generation and checking needs to be timely as well. So, what does the future hold? We want to add more solvers to our portfolio, solvers that do well, that are correct, fast, and stable. So, speaking of stability, how do we get more solvers? We spent quite a bit of time encoding our AWS access control policies into SMT. And we update this encoding as we expand to more use cases or when we support new features in AWS. This is again a slow and careful process that requires expertise in understanding AWS and understanding how SMT solvers work. There's a lot of trial and error to figure out what encoding is correct and performant. So this is an experiment we did on solver runtimes with different ordering of clauses. And we used the SMT competition shuffler to get the different ordering of clauses. Each point on the x-axis corresponds to a single problem of the instance. So we ran it in its original form, the default encoding, which is the base time, and 5 shuffled versions. So this gives us a total of 6 versions of the problem where we record the min, the max, and the mean times. And you can see in CVC4, there's a bit of distribution. Now, in CVC5, the distribution changes dramatically because there is a whole lot more variance with the different encoding orders. And yet another shape for what it looks like for Z3 sequence. This is not the end of it. We ran an experiment for how the different configurations impact the runtime in SAT queries. And, and we see, again, there's a whole bunch of variants that impact the stability and predictability of the services using the underlying SMT solvers and the configuration. So here it's just the different CVC5 configurations. These are all for SAT queries.
Based on our experience of generating a billion SMT queries a day, I want to talk about some general areas of research for the community. And I believe these are key to enabling the use of solvers to evaluate security controls, enable applications in emerging technologies such as quantum computing, blockchains, and bioengineering. Some of the areas of research were based on the challenges we've encountered. One was the lack of stability, monotonicity, and predictability in runtimes of a given solver version and across different versions. And this is a hard problem, but due to the inherent randomness in SMT solver heuristics, search strategies, and configuration flags. Some approaches here could be to incorporate an algorithm portfolio, do parallel and distributed SMT solving, or even move towards specialized solvers. Now, generating a billion SMT queries is the result of exceptional work and innovation of the entire SMT community over the past 20 years. And a question we are thinking about is how do we replicate the success described here for other domains in Amazon and elsewhere? And there is a natural tendency in the formal methods community to target tools for the expert user. And this limits broader use and applicability. If we can find ways to lower the barrier to adoption, we can gain a lot of traction and improve the security, correctness, availability, and robustness of more systems. SMT solvers are powerful engine, and one research direction for the broader community is to provide more higher level abstractions, better higher level languages to allow people to solve or to specify their problems. And also, all SMT solvers should be generating proofs to help the end user gain confidence in the results. I hope you are now convinced, as I am, that we are entering in the golden age of automated reasoning. As we move to a hyper connected world of IoT devices, cloud systems, flying cars, and talking robots, proving the correctness of these systems is going to be critical. And to achieve this goal, the field of automated reasoning will need theoretical innovations application of ideas, and robust tools. We will need it all. And the onus is on all of us to make this golden age of automated reasoning real. Your scientific innovations in the next 10 years will pervade all aspects of our life and society. So, thank you again very much for this opportunity to give this talk. Thank you.